So on this conference, like most of the things that are being done are like very far away from real life, because in real life you don't have like examples and answers, right? It doesn't work like that in real life. In real life, you take decisions and you get some rewards in the future. Much later, you go to university and you have first money because you went to university much later. So, and like this pig, it's like climbing the stairs, and hopefully up there is a reward, but it can't know if it's gonna be there or not. So, small pig has a giraffe that helps her to persevere and actually go up, climb. So this is pretty much what reinforced learning is about, and this is what I'm gonna show you soon. So I'm Maciej. I deal with deep learning and reinforcement learning, and this is exactly what this talk gonna be about. I had privilege to work with a couple of companies, including Berlin companies, lately. But yeah, let's go straight to the topic. So what can you do with reinforcement learning? Let's see a couple of examples. Let's start with funny ones. So this is, for example, a robot taught with reinforcement learning to play table tennis. Well, it doesn't do like a great job. It wouldn't win with a master of table tennis, but still, it learned a reasonable strategy, right? Especially if you take into account that the only input for learning here is a video. So it actually, the arm here records the video and it responds asynchronously to the input. Now, next example, stop it. Technology. So you might have heard about AlphaGo. Google DeepMind won with a master of Go 5-0 using one part of the solution was reinforcement learning. They put it all together with like supervised learning and a bunch of other stuff. Really crazy thing. Another thing you can do, and this is actually my favorite one so far, is, for example, is creating, like finding objects on an image. So what people would usually do is they would use simple neural networks for doing this. There's a couple of problems with that. One is that it takes a lot of time because the neural network needs to look like at each, say, part of the image, like pretty much sequentially, to figure out is there the object there or not. And you need to stride per like a couple of pixels at a time, so it takes a lot of computer power to actually do this. So what you can do instead is to create a game out of this problem. And the game is, you can zoom in, like here, you can zoom in the image, you can move the image right or left, you can zoom out the image, you can move the image, you can move the bounding box up or down, and you can stretch the image, you can stretch the bounding box. And each time you're doing this move, you're getting some reward. And the reward is roughly the distance from the true bounding box for this cow in our case. And it turns out that this approach is actually not only faster than traditional approaches, but it's also more robust. It simply works better. And what I did, I played with this concept and I re-implemented the original paper that introduced deep learning, and I started to play Space Invaders, and that's how it goes. So you can see it's not like extremely good, but if you think about it, like the input for the algorithm is exactly the screen frames. And the only thing that the guy can do are to take actions. So the actions the guy is doing here is go left, go right, or shoot, or do nothing. And so it knows nothing. It actually, I never told him that this button moves the ship to the left, or this button moves the ship to the right. I never gave him any clues about what the game is about, actually. The only thing that he gets as an input apart from the frames is the score. So it actually can see that some actions brought him like additional rewards. Now, this is how the training progresses. So you can see that after 100 epochs, which in my case is about 5 million actions taken by the neural network, it achieves like pretty reasonable result, and then it kind of flattens out, but it keeps learning anyway. And this is like distribution of the game rewards. The funny thing here, if you're interested why it keeps like why it's so dense here, that's because it's like the end of the game. So like 600 points is pretty much the point where he reaches the next level. So he's very good at getting there, and since the spaceship started moving faster, then I don't know, he's not so good at like jumping over this level. And like you can do something like that too. This is actually Doom, and this is exactly the same algorithm. Like pretty much not a single line of code changed. I mean, nothing really good. You can see how good it is at aiming. It's not, and the strategy is reasonable. He keeps turning left. That's what you would do anyway, right? Because I mean, in this scenario, you can only turn left or right and shoot. So the best strategy is to keep moving in the right direction, right? The same direction. Oh my God. This is fun because here you can see what the agent actually sees. So he doesn't see the color frames. It's just grayscale, and it's scaled back to like 80 by 80 pixels. And in this scenario, the goal is to avoid the fireballs shoot at the agent, and he is extremely good at that. Like. He really does a good job. Okay, I could show you more of that, but maybe let's go straight to the point. So how does it work? So as I mentioned earlier, it's all about the rewards and not actual, truth. Because there is no truth in our world. We don't know whether this move is like the best move or not. It's hard to say. It's very hard to implement artificial intelligence playing Space Invaders that would be as good as that, based on the input only. So how does it work? So first of all, we have a world, and in our case, we have an emulator of the Space Invaders. And this emulator, once we give her the frame, once we give her the action for a given frame, so we are in this state. That's what we see basically. Then we take an action, and the emulator gives back new state, so the new frame, and the number of points that we got by taking this action, and the information whether we lost a life or not. Now, what we can do with it is, so it's simple to imagine that our goal is actually to create a policy, a strategy, that given a frame, we want to take an action. So, for example, so how to do that? So there is this concept of Q-learning inside of like part of reinforcement learning is all about Q-learning, and very briefly about that. So we want to construct a function that, given a state, in our case frame, will end like any of the actions that I can take, will give us an estimate of how good this action is. Once we have that, but what does good action mean? That's like not very well specified, I know, but we'll get there. But given that, we can very simply implement a policy, because all it takes is actually saying that we want to take the action that gives us the biggest Q value. So let's do it like this. So we can think about, so like in Q-learning, our goal is really to accumulate as many rewards until the termination of the game as possible, right? That's the goal in our lives, pretty much, as well, more or less. So we keep taking the actions, we keep getting the rewards, and we would love to define the queue as this equation. The problem is we don't know what the future is going to give us, right? We don't know what's going to happen in the future. So we don't know what the reward is going to be in the future. But we have a nice insight here, which says basically that this expression in the brackets is nothing else but the queue function, but in a new state. Right? So how does it work? So we are in a state. We are living in a state right now, and we wonder what's gonna happen. How to put it in words? Yeah. So we're in this state. We take an action. We have an estimate of how many points we're gonna gather throughout the game. Then we take an action, and we're in a new state, and we can ask the same question. So how many points am I gonna get until the end of the game? Now, if these estimates differ, I mean, these estimates will differ, but if these estimates differ a lot, then we would say, hey, we are surprised, right? We expected that by taking this action, I will get this much reward. I took the action, and now it seems that I'm going to get less or more. And this is important. This notion of surprise is very natural, because that's what happens in real life, right? You cross the road, and if a car hits you, then it's like, oh, yeah. Next time I will think more carefully before crossing the road, right? And that's exactly what's happening here. So how to put it in math back again? So we said that in like the ideal world, we would have an equation like that. That's what I described a minute ago. But we don't have that. We need to get there. So how to get there? So we want to have an estimate of Q. I will call it Q hat. And Q hat is supposed to be an estimate. And now we define the surprise as exactly what I told you. Now, why is it so important to have this surprise? Because this surprise, you will see it in a second, will help us define loss function for our neural network. Let's get there. So neural network, as you know, is basically a very complex function. It's nothing more. It just takes an input, gives an output. It's very complex, and we know how to teach it. In my case, it's a couple of convolutional layers and 2 dense layers. The important thing is that the output of our neural network is supposed to be the values of the Q function, so the estimates of how good this move is going to be. Yeah, and the surprise that we defined a second ago is exactly the loss functions we're going to use. Now, the funny thing here is that in a supervised learning setup, what you have is x and y's. And your loss function is a function of x's and y's. Here, the loss function keeps changing, because the loss function is defined in terms of the Q in a twisted way. We have Q here twice. We have the output of the network like done in a slightly twisted way, but it works anyway. Yeah, and there is still a couple of problems if you want to play Space Invaders or any other games, because a single frame is not enough to actually understand what's going on. You don't know if this laser beam here goes up or down, which might be actually crucial information, right? So what you do instead is you put a couple of frames. So you want to input a couple of frames instead of a single frame. Now, so usually, in neural networks, you have this tensors of inputs, right? So your input is usually like 4-dimensional tensor. And the second dimension is usually used for RGB channels. So instead here, we are using these channels to stack a couple of frames, one on top of the other, so that the neural network has access to information, not only the current frame, but also 3 previous frames. And this helps a lot. This actually makes the neural network learn much faster and much better. There's a couple of other details that are funny. So when you teach a neural network and you're using SGD, stochastic gradient descent, then one of the most important things is that you keep the mini batches decorrelated. Otherwise, SGD is not going to work. It's going to, converge to something weird. So it means that we can't really use last 32 experiences to feed into the neural network. So back in '93, someone came up with the idea that instead we're going to keep the experiences in memory, and the backpropagation step will not be based on like the last 32 frames seen, but will be sampled from the memory. So we sample the experiences from memory, we put it through the network, and then we do backprop, and that's how we learn. Also, an important thing is exploration. So reinforcement learning is a lot about exploration-exploitation dilemma. In order to be able to exploit the world, you need to explore first long enough, right? That's what children do. They keep running around and exploring, and it might be overwhelming how they explore the world, but that's the only way for them to learn. Now, after some time of exploration, we want to start exploiting the strategies that we learned, because after all, we are here to gather as many rewards as possible. So in this case, the exploration is very simple. We just flip a coin at each step, before taking action, we just flip a coin and we decide, okay, are we going to explore or are we going to exploit? If we decide that we explore, then we flip a coin again, and we choose the action that we take. This exploration, this epsilon, governs the probability of coin flip, and of course it decays to some 0.1 or something. Okay, I'm not gonna speak about other details. Now, my implementation is actually available out there. You can grab it, you can run it for a couple of days before something useful comes up. Good luck. So I did in Tiana and Lausanne, I did in AWS on Spot instances because I'm cheap. Yeah, and like I write here, like it takes about 36 hours of training to be able to say, okay, it does a good job, or okay, it's really crappy. It took me about 40 rounds to achieve those 1,000 points threshold, pretty much, because I kept improving things, and there's lots of tiny details that if you omit, or if you don't realize that they exist, then things are gonna perform worse than expected. Yeah, that's basically it. Oh, I was so fast. I can show you the other Doom games. That's gonna be interesting, right? Yeah. So this is, for example, a scenario of when you need to gather the medikits. That's the whole point of this thing, and it does pretty much a good job. When it sees the corner, it keeps going left to actually turn around, which is pretty crazy actually. And then it just keeps going. It's awesome. And this one is also fun. I'm not sure you're gonna see something here, but here on the left there is a guy, and the goal is to shoot him. Now, obviously we don't see him very well, but actually the neural network does. So, and it does pretty good job. So it's hard for us to judge how good job it does, but yeah, maybe you can actually. Yeah. Okay, going back to the thank you page. Thank you.
Raise your hand if you have a question.
Here we have some.
Thank you for the interesting talk. I've only played around with queuing a little bit, and the one thing that I've had a problem with is that I needed to tell it for every state at every possible action it can take, and then how much reward it will get. And that gets very complicated very fast. Maybe I did something wrong, but how do you actually estimate the reward for an action if you don't really know what it's going to be?
Yeah, I mean, in this case, we simply take a look at what the score, the actual score is, and what the score was in previous step, and we take, a difference, and that's the reward for this action.
But how do you know that beforehand? Like, do you want to? But what I don't understand is how you want to know before taking action what's the best action.
Yeah. Okay, I see what you mean. So it's all about this, like the estimate. So the neural network is supposed to estimate this ideal Q function, and I don't know, and that's it. No, I'm sorry. It's just it's fuzzy. It's not that easy to explain. So Q function. So if you imagine the Q function, by definition, is like the expected accumulated future reward, right? Then your question is has no ground. I mean, it is. I mean, if it isn't, then our estimate is poor. But we still treat it as it was accurate. Does it answer your question?
I'm not 100% sure, but I need to think about it more.
Yeah, I mean, it's tricky. It is. It takes a little bit of time of reflection to actually realize what's going on.
Hi. Oh God, it's loud. You were talking about channels before, and you said normally there are four. You'd mentioned 4 dimensions, and one of them was RGB.
Yeah.
What might the other channels be, or what would the other channels be?
Yeah,
I'm a total noob.
So normally you can think about an image. So a black and white image, a grayscale image, is a 2-dimensional thing. Now, colored image is a 3-dimensional thing because you have 3 channels: red, green, and blue. Now, in our case, we consider only grayscale image. The frame, we just ignore the colors and we make it grayscale, and then we stack one frame, previous frame, previous frame, and previous frame, right? Now, the first dimension is the batch dimension, so you just put 32 of such images. So that's why you have batch channels, height and width. That's what you put into your neural network usually.
I think, didn't AlphaGo lose one of his games? Or her
Sorry?
games? AlphaGo lost one of his games.
Well, there were actually 2 matches with 2 master goes. Yeah. And the first one, actually, AlphaGo won, but the second one, there was 4-1. But it was with another Go master, yeah. There was another question over there, I guess.
Yeah, thanks for the interesting talk. I was just wondering, why does it help to actually include in Space Invaders the 3 previous, or how many previous frames it was? Because if you would just model, like if you would just have, well, the one basically shot that goes in the other direction from your defender, or I don't know how I would call it. Sorry, I've never played that. It's like if you would just make it in a different color, then shouldn't like the algorithm figure out by itself which direction it should be moving and the rest?
Yeah, but we don't want to change the game in any way. We don't want to modify the game. We just want to apply the algorithm to all the games that are out there
I guess I see that. But like, if you would have a different color, then we wouldn't need the previous frames anymore.
Yeah,
right?
absolutely. The previous frames is done here. It's a technical trick to make the neural network aware of like time. You could also use some recurrent neural networks, and that's actually what was done. And then you can avoid this trick. But it's faster this way, and it's like slow enough this way anyway.
Thanks a lot. How does the model work with the problem that the reward is actually coming in a lot of steps later? Like when you shoot upwards, you hit whatever the monster is there, like 10 frames or 20 frames later.
Yeah, that's a very good question. Thankfully, we have the right slide here. So. Okay, we can actually take a look here. So it's all about, our kill function. So take a look here and imagine if gamma was 0, right? So if gamma is 0 in this equation, then all we take into account, all we want to consider is the nearest reward. And then we are not going to learn too much because we're going to take actions only to take the nearest reward. We're not going to really think about the future. But if gamma grows, and actually, usually people set gamma to 0.99, so it's decaying very slowly with time. If you take a look at this equation, it means that the rewards that are farther away in time are considered as a little bit less important. But on the other hand, they are there. So if I shoot my laser beam right now, I will get some, and the spaceship gets destroyed in 10 steps, in 10 actions later, then I will get for that gamma to 10 times the reward. So it's still going to be a pretty huge reward. Does it answer your question?
Yeah, thanks for the great talk. How sensitive is your model actually to the hyperparameters like gamma or epsilon from your epsilon greedy strategy?
Yeah. There is just about 20 parameters. I didn't mention most of them. That's a good question. It is. I mean, there are some parameters that are extremely important. I would say that gamma and epsilon, yeah, you will see difference, but it will work anyway. I mean, of course, if you set gamma to 0, then it's not going to work. But if you change it by 10%, well, it would work. Maybe slightly worse, but it would work. Now, there are some parameters usually related to stochastic gradient descent. And here, the stochastic gradient descent was actually performed using RMS prop, so-called DeepMind RMS prop, very well-hidden algorithm that you can barely find around, but it exists. And there, for example, changing this by 20% just destroys everything. There's just a very tiny island of convergence of the neural network. If you don't put it right, then it's just going to diverge very quickly. But that's the nice thing. It's going to diverge extremely quickly, just in a couple of minutes. Yeah.
Have you tried setting gamma to values greater than 1?
It's gonna diverge by definition. In Q-learning setup, you never consider gamma greater than 1. I mean, even 1 is tricky, and you can't use it always because if your game that never terminates, then your Q would converge to infinity, and it doesn't make sense.
Okay, this may sound like a total noob question, but how did you actually let this guy play the game? Like, did you have a robot hand that moves the joystick, or did you just
no.
look into the keyboard input? Or how did you actually do it?
So there was actually there's actually an environment created called I don't remember how it's called, but anyway, arcade games learning environment where someone actually took the Atari emulator and exposed an API through which I can interact with the game.
Okay.
And the same trick with Doom. There is also an API created, and you can interact with it. You get the information about how many points you got, etc.
Okay, and the second question, if I may, what is the most complicated game somebody has already achieved?
Well, AlphaGo, I guess.
Pardon?
but sorry, Go, right? The thing that I
mean,
show.
computer game.
Well, you can have Go on computer. I don't know. It's a funny question. I don't know. We played recently with Doom. That's pretty complex. You have 3D world. There are totally new challenges. The scenarios that I showed you here are pretty simple. But if you imagine like a deathmatch scenario when you have 50 possible actions, if you take into account like changing weapons, etc., it turns out it's like 50 possible actions. And you have like there are completely new problems because you don't see the world as a whole. So here we had like partial observability, but only in terms of time. Whereas in Doom, you look at a part of the world and it's very tiny fraction of the world. So how to handle that? That's, I guess, not exactly closed question yet.
Thank you.
Are techniques like this actually used for bots in shooters, or are you planning on doing something like that?
Well, what do you mean bots?
Yeah, computer plays.
No, I never heard about it. I don't think so. They should, but they could. I mean, it would be impossible to win with such bot. I mean, in Space Invaders, the best can achieve like 9,000. The best implementations with like a couple of additional tricks can achieve as much as 9,000 points. Which, for me, frankly speaking, I mean, I wasn't able to achieve like 1,500. That was completely beyond my capabilities. Of course, I'm not an expert, right? But generally speaking, like this deep Q learning gets in most of the Atari games, there's like 50 available, gets better than the experts.
Okay, I have a question. What are the advances in some card games, like let's say poker, and using the same framework, just the score or the function would be calculated on the, let's say, monetary value of your stock, let's say?
Good question. I don't know.
Any more questions? We still have a couple of minutes. Okay, so thank.
Oh, there's another one.
Love it.
No, maybe I can comment on the poker thing. So I guess it's gonna suck hard. So when you try to solve poker, usually what people do is some game theoretic approaches like counterfactual regret minimization, where you have a better model of the game and where you can like converge to a Nash equilibrium quite fast. Because I guess usually in poker the problem is that the game set is super big, and I don't know. Here it's still manageable, I guess.
Well, it differs how you look at it. If you, I mean, you took like the frame is 320 by 160. Of course, we can resize it to 84 by 84, but still, the number of states in theory is like 1600, plus the time frames, which is 4 times 4, so it's 6400 like inputs. Then, of course, the convolutional layers compress it to something like 200 features. But I really don't know the answer.
Yeah, in poker you get more states than atoms in the universe.
Yeah, I'm not that good in poker. Maybe I will not just that.
Okay, so thank you, Matthew, very much.
Yeah, I mean. So if you wanted to play with that, I will post this presentation online. I mean, it is already online. I just post it on Slack for you. If you have any questions, feel free. And there's lots of good links here.